want to eat any more rice or should I put it away?
I just like shoveled food in my face before I sat down.
I now call to order the Society's 2,431st meeting in the 149th year since its founding on March 13th, 1871. Good evening, everyone, and welcome to another installment of the fall lecture series produced by PSW Science. Because of COVID-19, the Society is bringing these meetings to you via Zoom from locations all around the globe, rather than our usual home, the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C. Tonight, we will hear about chemistry at ultra-cold temperatures, assembling molecules atom by atom. Our speaker is Kang-Kuen, Morris Kahn Associate Professor of Chemistry and Chemical Biology and of Physics at Harvard University. I'm Larry Milstein, President and Program Chair of PSW Science, one of the oldest scientific societies of Washington, D.C. PSW Science is a 501c3 nonprofit education and science organization whose mission is to provide a forum to exchange scientific ideas, further scientific understanding, and encourage scientific inquiry. This lecture is being recorded, and it will be posted to the PSW Science YouTube channel, where it will join over 150 other recordings of PSW Science lectures. We invite everyone to take a look and explore these presentations, and to become a member of the Society through the PSW Science website, www.pswscience.org. Membership is a foundation of the Society. I encourage everyone with an interest in science to join. The Society is grateful for the sponsorship of the 2020-2021 lecture series by the Policy Studies Organization in cooperation with the American Public University and by a generous donor who is asked to remain anonymous. PSW thanks all of our sponsors and all of our supporters. And we wish everyone in this season a very, very happy holiday and all the best for the new year. Before we turn to the lecture, it's the tradition of the Society to welcome new members and read the minutes of the previous meeting and the summary of the previous meeting's lecture. I am pleased to announce that our speaker tonight, Kang-Kuen, has been elected to the Society. She learned of PSW through our invitation to give tonight's lecture. And her interests in some small part will be clear from her lecture tonight. We welcome her to membership. Recording Secretary James Heelan will now read the minutes of the 2430th meeting and the lecture by Christoph Waldmann. His lecture on the German triple project to Europa is available for everyone without charge on the PSW Science YouTube channel, the PSW Science Vimeo channel, and it can be accessed directly from the PSW Science website, www.pswscience.org. James, the screen is yours.
Thank you, Larry. On December 4th, 2020, by Zoom video conference broadcast on the PSW Science YouTube channel, President Larry Milstein called the 2430th meeting of the Society to order at 8:02 p.m. Eastern Standard Time. He announced the order of business and welcomed new members. The recording secretary then read the minutes of the previous meeting. President Milstein then introduced the speaker for the evening, Christoph Waldmann, Triple Project Co-Director and a research group leader at the Center for Marine Environmental Sciences at the University of Bremen. His lecture was titled The Triple Project, a system to explore Europa's icy oceans. Waldmann is co-director of the Technologies for Rapid Penetration and Subglacial Lake Exploration, or TRIPLE, a 5-year project funded by the German Aerospace Agency. TRIPLE aims to develop and build a dedicated tool set to explore oceans and lakes on planets and moons of our solar system, with a focus on one of Jupiter's moons, Europa. The technical feasibility of this tool set will be validated in Earth analog environments, such as the Antarctic Ocean and subglacial lakes. The Galileo spacecraft, launched in 1990, identified a dipolar perturbation in Europa's induced magnetic field, revealing the existence of a liquid water ocean below the moon's icy surface. NASA is currently in advanced planning for its CLIPPER mission to further study Europa. CLIPPER will carry cameras, ice-penetrating radar, a magnetometer, an infrared instrument, and other instruments that will seek any material that may spray from the ocean as plumes into space. The European Space Agency is also planning the JUICE mission to orbit Jupiter. Waldmann said the natural evolution of Europa exploration will be to land instruments on the moon's surface and eventually to conduct ocean exploration. Exploring Europa would include a search for and an effort to gather evidence of biosignatures, habitability, and surface properties and dynamics. Scientists are focused on Europa over other icy worlds in our solar system because Europa has an energy source, biologically essential elements, twice as much liquid water as Earth, and significant time without major alterations. Together, these elements suggest life has had sufficient opportunity to develop. Waldmann said the CLIPPER and JUICE missions should provide scientists with high-resolution images to identify a safe location to land a future exploration mission. Once landed, an ocean exploration mission will still need to pierce the moon's approximately 10-kilometer thick surface ice, maintain operations and radiation, and move in the deep ocean environment. Triple aims to provide the tools for an exploration mission to navigate these post-landing steps. Due to Europa's hydrodynamics and energy supply considerations, Triple proposes to melt 10-centimeter holes through Europa's ice and explore its oceans with a small underwater vehicle. Current probe designs are able to melt ice at a rate of only 2 to 6 meters per hour. At these rates, the probes would require 200 to 600 days to melt through Europa's surface ice and would require approximately 10 megawatt hours to accomplish. Once deployed under the ice, Triple's system will need to balance the need for good surface-to-vehicle communication with vehicle autonomy. Triple proposes for the melting probes to deploy a puck radio frequency operated electromagnetic wave relay system as the probes bore through the ice. These pucks would communicate to a surface lander, which would communicate with an orbiter. Because there will be a 33 to 53 minute delay in communications between Jupiter and Earth, the underwater exploration vehicle will require significant autonomous operations control. Once deployed, the vehicle will need to rely on sonar systems to orient itself in the dark and navigate significant tidal currents. Because these currents are predictable, Waldmann said properly timing the release of the exploration vehicle could mitigate the problem. Triple's current prototypes for a nano-autonomous underwater vehicle, or nano-AUV, are inspired by glider-type vehicles currently used to explore Earth's oceans. The nano-AUV will need to reach depths of 12,000 meters, move at approximately 1 meter per second, and be light in weight. Triple is still considering whether to use wings, jet propulsion instead of thrusters, and what kinds of sensors to mount on the nano-AUV. Waldmann then discussed the issue with underwater sound propagation. Sonar navigation is problematic because the surface ice will reflect more sound than an Earth-like open-air ocean. The Doppler effect is also more pronounced in water. To address these problems, Triple is exploring bio-inspired approaches toward underwater communication. Triple is currently planning an Earth analog mission to test the validity of the tools it is designing. Waldmann said 2030 is the earliest a Europa mission could launch. Such a mission would arrive in orbit in 2037, melt ice until 2039, and begin ocean exploration in 2040. The speaker then answered questions from the online viewing audience. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 9:48 p.m., President Milstein adjourned the meeting. The temperature in Washington, D.C., 9 degrees Celsius. Weather, rain. Concurrent viewers of the Zoom and YouTube live streams, 92. And views on the PSW Science YouTube and Vimeo channels, 294. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. The minutes will be posted to the website in due course. Please send any corrections or comments on the minutes to corresponding secretary Robin Taylor at correspondingsec@pswscience.org. We now turn to tonight's lecture, and it is my pleasure to introduce tonight's speaker, Kang-Kuen, who is joining us from Boston, Massachusetts. Kang-Kuen is the Morris Kahn Associate Professor of Chemistry and Chemical Biology and of Physics at Harvard University. Her group pursues innovative approaches to using lasers and magnetic fields to bring molecules to a standstill. In particular, they create and gain quantum control of molecules for the study of chemical reactions, quantum information processing, and quantum many-body physics. Kang-Kuen earned her PhD at the University of Colorado Boulder. All questions will be fielded after the lecture during the Q&A session. And with that, the screen is yours.
Thank you, Larry. Let me share screen here. Great. Hello, everyone, and thank you for the thank you, Larry, for the kind introduction and the invitation, and thank you, everyone, for joining me. It's my great pleasure and honor to spend this evening with you to take us all on a journey to the extremely low temperature land we call ultracold regime. By that, I mean a temperature at around microkelvin or below. In particular, the story that I will focus on today would be an almost science fiction-like capability of grabbing exactly one atom using optical tweezer, as I show in these pictures. This is a single atom, picture of a single atom, and to build one molecule atom by atom, as shown pictorially in this picture. There are many reasons for our scientific pursuit to gain such an exquisite control of atoms and molecules, and one of them is to build a quantum bit, so-called qubits of 1 and 0. Because we're trying to gain all quantum control that we can on atoms and molecules, let me start with a little bit of background information. Let's see. Okay. All right. Okay. Seems like I have to do the spotlight every time. Okay. All right. So quantum mechanics 101. These are things that I will be talking about, and I'm sure most of you are familiar with, but just to make sure that we're on the same page, I wanted to review these ideas. Quantum mechanics, sort of the signature of quantum mechanics, of course, is that the energy level of a system, for example, a hydrogen atom shown here in Bohr's model, the energy levels are discrete. So in such a model, electrons has these discrete energy level that it can hop to. And in between there, there's no orbit, so it cannot go in there. So to talk to the hydrogen atom, for example, in this case, we had to shine energy into the system at exactly the energy difference of different discrete energy levels. Once the electron hop onto an excited state, it could also emit a photon, let's say, and hop back down into a lower energy state. A way to describe, such discreteness of energy level is through the wave-particle duality. So in quantum mechanics, we can also think of particle as waves. Okay, let me just turn off this spotlight here, because it interferes a bit with the next slide. Okay, so all right, so to think about these, to support these discrete energy level, we can think about particle as waves, and there is a characteristic wavelength that we can that characterize the particle, and that there has to be sort of integer number of wavelength that can fit around these orbit. For example, for n equal to 3, we have 3 waves shown here. This is 1, and that's 2, and that's a third one. And 4s or 5 or 6, and so on and so forth. And because we describe particle with wave now, that there is uncertainty associated with. There is a wavelength associating with the particle, so we can no longer talk about the exact location. There's always some kind of uncertainty sort of associated to the wavelength of the particle. Because we describe these particles as waves, they are very intriguing property of them. For example, superposition that actually will become very powerful, as I will get more into the lecture. For example, if we have 2 waves, wave 1 and wave 2, we can superpose them. We can do linear combination of wave 1 and wave 2, and the resultant wave looks like the following. These are properties of the waves, and that is what we use to describe particles in quantum mechanics. Okay, so today's lecture is going to be about molecule. Everyone has a notion about molecules and think about them differently. I think of molecule as perfect quantum machines, and they have many degrees of freedom, which I use the word quantum degrees of freedom. And these quantum degrees of freedom give different unique transitions. For example, the electrons in the molecule can go to different orbits. These electronic transitions gives a certain fingerprints of the molecule. But that's not the only energy difference levels that exist in molecule. In the simplest case, we can think a molecule made out of 2 atoms, and that's for basically what we will be considering today. Molecule can vibrate, and that energy levels are also discrete. And if we look more in detail, if we zoom in the vibrational levels, we'll also see more discretized energy level that corresponds to the rotation motion of the molecules. And if we look in there some more, we'll find the spin degrees of freedom, hyperfine levels of molecules. As I already said, that all of these transition gives unique fingerprints and ways for us to probe them. And in the chemistry domain, these degrees of freedom allow different imaging tools. For example, stimulated Raman imaging of vibration transition get molecular specificity under a microscope. In this example, these 2 images have the same field of view. But on the left-hand side, we have the conventional optical microscope image. And on the right-hand side, we had these stimulated Raman imaging to tell us the molecular content. And you can see that they look very different. It gives a lot more information once we know the molecular content. For example, in this region, we have a protein-rich tumor. And over here, we have lipid-rich white matter. So you can see that knowing the molecular content gives a lot more information. Now, another example would be that widely known is the nuclear magnetic imaging, magnetic resonance imaging. And here I show you examples where in these images, they identify where water is in the cob of corn. While molecular quantum degrees of freedom allow us to identify and study molecules in their innate environment and generated these widely used tools in chemistry, biology, and medical setting, in the physics domain, these characteristic transition frequencies allow us to use them as standards for time and meters. So I want to speak a little bit about atomic clocks. I understand that there are experts in the audience. The first atomic clocks was in fact based on the vibration of ammonia molecule turning itself inside out at 24 gigahertz. In this excerpt from Popular Mechanics 1949, it says that this was the first clock that does not depend on astronomical observation. And it was so accurate that it will lose only 1 second in 300 years. The more modern atomic clocks, now they are based on vibration of electronic density. So let me show you an animation and how these intrinsic frequency in molecules or atoms connect to the ticking of a clock. Okay, so what we see here is the familiar S&P atomic orbitals from first-year college chemistry and physics. These orbitals are waves, like I shown you in the quantum mechanics 101 slide, but they have very different spatial pattern. When we drive a transition halfway to bring the atoms in a superposition of S and P, that is, we add then with a special phase factor and take the norm square. Now we can see the ticking of the clock as the moving electronic probability density. I'm showing here 10 to the 15 times slower than it normally runs. The same picture that I show you here in terms of bringing 2 waves, adding 2 waves, adding 2 state and 2 waves into superposition will also apply to quantum bits or other quantum system. Atomic clocks have advanced Significantly, since 1949, I believe in one of the prior PSW lecture, Andrew Letlow came to present on the current state of the art clock. Nowadays, these clocks would not lose a second in a time longer than the edge of the universe. So very accurate, of course. This is enabled by the development of quantum control techniques that allow the atoms to tick at their natural frequency without any perturbations, or minimize the perturbation as much as possible. Major enabling technique includes laser cooling of atoms to their lowest quantum mechanical allow temperature. So they are frozen and not Doppler shifting the transition. So let me tell you a little bit about laser cooling, because that's really a workhorse of the sort of the thing that we're working on. And I was told that Bill Philip might be in the audience, so I'm sure you'll know that he got a Nobel Prize for laser cooling of neutral atoms. Okay, so here is laser cooling in a nutshell. Say we have an atom, or we have an object, we have an atom that has a mass of m, traveling at some speed of v. It can interact with photons, especially it can interact with photons that will be the specific, that will talk to the electrons, the specific frequency. So they can absorb a photons, and after it absorbs a photon, the photon carries momentum, so it absorbs photons, so it loses a little bit of speed, it loses a little bit of momentum going to the right. Now, very quickly, these excited electrons will emit the photon and go back down to the ground state, and there will be another photon emitter. So a total of sort of 2 units of momentum of the photon will be transferred to the momentum of the atom. And that's laser cooling. But of course, to cool down from room temperature down to sort of hundreds of microkelvin temperature, one will need a lot more photon. So the analogy would be the atom is like the bowling ball. It's very heavy. It has a lot of momentum because it's very heavy, it's moving. And we're throwing photon at it, and we're actually throwing ping pong ball at it, and we need to throw millions of ping pong ball in one direction to slow down the direction that the bowling ball was going. So this is a way, so basically cycling photon is essential, cycling photon to sort of million times is essential to slow down atoms from room temperature to hundreds of microkelvin. Okay. Now, laser cooling and other techniques had led to a whole new and exciting direction of the field, atomic and molecular physics and chemistry. Specifically, I want to focus on quantum control technique applied to a molecule that allow cooling and trapping of molecules inside vacuum chamber where we can probe them. Laser cooling to molecules are, of course, much more challenging, and the reason is because molecules have all these quantum degrees of freedom that I alluded to in the earlier slide. It has vibration, rotation, and spin, and its motion. And I also put down the sort of equivalent temperature scale of the energy, just because I like to use temperature as a gauge, because we're working with ultimately sort of microkelvin temperature in terms of motional degrees of freedom. So because of all these degrees of freedoms, that it's difficult to cycle photons repeatedly, because often that once a photon is absorbed in the molecule, it can go into the states that could no longer absorb the same color of photon. So laser cooling of molecules is actually very challenging. So what I will tell you in the technique that we will use, we actually cool the atom and try to make the molecules out of the very cold atoms. Okay, there are a number of scientific directions under sort of the big umbrella of motivation of using these very, very cold molecules, starting from sort of searching for new physics. So looking at the structure of the molecule, make very, very precise measurement, we can reveal something about sort of general framework of physics, and it could even at least put constraint for search of physics beyond the standard model. One can also look at fundamental aspect of chemistry. Chemical reaction ultimately boils down to a quantum mechanical process of exchanging bonds. So can we understand such a process very precisely? Purely using the language of quantum mechanics is one frontier. One could also use them in these sort of order array to simulate very exotic material and perhaps even to compute, to take advantage of the quantum resource for very for much more powerful computational power. So let me just give you one advantage of quantum computers. There are many, and it's not the focus of this talk, but this is some very simple ideas. I think it sort of illustrate the powerfulness of what quantum computers will be in the future once we have them. And this sort of lies in the principle of superposition. Okay, so quantum computer can compute at very high dimensional space. And the reason can be understood as the following. If we have classical bits, say we have n bits, we have n dimensions of, it can compute in n dimension, let's say. And if we have quantum bits, and if we have n bits, then we can compute in n 2 to the n dimension. And why is that? Here I want to illustrate those points. If we will have a bit, this bit is 1 or 0. The unique things about quantum mechanics is that the system can be in a superposition of 0 and 1. So in a superposition of 0 and 1, you can think of these are different waves. That means there's different linear combination of the 0 and 1. So now, because the system can simultaneously be in 0 and 1, and we can describe it with these two coefficients, alpha and beta, we have actually 2 bits of info, like we have 2 dimension, we call 2 dimension of information. Even though it's just 1 bit, there could be 0 and 1, or a superposition of 0 and 1. And if we have 2 bits, 2 quantum bits, and now you can see we have 4 coefficients in front that we can specify. So we now have 4 dimension, 2 to the 2. And if we have 3 bits, and now we have 2 to the 3 dimension that we can use to compute. And you can see that this dimensionality can grow very, very fast. And that's sort of the powerfulness of quantum computer, that it could ultimately, once we have them, to compute in very high dimensional space. Okay, so with polar molecule, with molecule that we are interested in, our quest to get very exquisite control of the molecule is that we want to make some kind of designer molecule for these quantum computation or quantum simulation platform. In particular, we want to take advantage of the very large variety of internal states, the internal state I spoke about, for example, rotation and hyperfine, to really fulfill competing requirements that we need for our quantum science applications. For example, in a quantum computer, we want these information to be able to store without perturbation. So we want a degrees of freedom where nothing can perturb it. But at the same time, we want logic operation, and that by nature, that means that the qubit need to talk to one another. So these are actually competing requirements. How do we realize such a a system with such competing requirement and do very good job for every single step? Our idea is to, along with many other people, is to use the different degrees of different quantum degrees of freedom of the molecule to serve the multi-purpose, the multi functions in a single package. Particularly, we want to store information in the spin degrees of freedom and allow them to talk to one another through their rotation excitation, through the dipole-dipole interaction, which is interaction thinking of these molecules as little magnets. These are electric dipole, different from magnetic dipole, but similarly, they can be repulsive or attractive, depends on their orientations. So this is a way for them to couple to one another, but they only gain these interaction when we put them in the right quantum states. Okay, so now let me get into the experimental side. So what we're have been pursuing, and what's sort of the main focus of today's talk, is that we want to build molecule individually and with all their quantum degrees of freedom control, such that we can encode information and we can get the information from one to the other and to the next one and so on and so forth. Okay, so as I had already mentioned that using laser cooling to cool molecule is quite challenging, and therefore we want to use laser cooling to cool atoms so that we can get these quantum degrees of freedom that I spoke about are all exactly controlled to be in a single quantum state. Okay. So in order to make a molecule, then this will be relying on chemical reactions. So usually if you have, say, two species, A and B, blue and orange here, you can see that to make AB molecules, they have to collide under the right condition, and some molecule will form after that. Okay. And this is sort of a very general description of all chemical reaction through collisions. Now, if we want to have individual particle control from the start, we like to go beyond these paradigm of, a bulk sample of atom A and a bulk sample of atom B, and through collision that they make molecule when they, when they're under the right condition. We want to control in such a way that we really can create a molecule, ideally more or less on demand and one at a time, which means that we really want to have, starting point of exactly 2 atoms and make a molecule out of it. Okay, so this is the experiment that we do, and we have been working on this for a number of years, starting with sort of proof of principle demonstration, which was a cover story in Science in 2018. So the general idea, the general approach that we take is that we use tweezers first, tweezer that made out of light, optical tweezer, to grab single atoms, 2 different species, and then we can steer them so that they will be together in the same tweezer as shown in the picture in the panel, starting with then trapping individually with optical tweezer into separate ones, and merge them into a single one, single confining potential provided by one optical tweezers, and then and figure out ways to convert the atoms into molecules, and then put the molecule in the right internal state, from something really far away, vibrationally excited, to vibrationally ground state, for example. Okay, so this is sort of the steps that we take to make the molecules, and this conceptually quite simple experiment is actually quite complicated to really accomplish. So here I show you a picture of the lab where we actually make this chemical reaction happen. And there is a saying about conservation of complexity, as you can see. So that the very simple, conceptually simple things that you're trying to do, that means you have to, in real world, you have to control all the degrees of freedom, every little thing, so that you can get to that condition where things are simple. Okay, so now, where does this experiment actually takes place? There's actually that glass cell, as I show you here, actually this glass cell where we vacuum chamber, where the experiment actually takes place, that is on this cover, is actually embedded over here. And very much covered by by all these mirrors and lenses, all these optics and lasers. So if we look from this from sort of the same view that we're looking at this, we see this glass cell, a cross section of the glass cell. And inside there, we have a little orange ball. And this, in fact, is about a million sodium atoms that has been laser cooled. And the laser that we use to cool it, once the atoms absorb the photon, they can re-emit, and that's the sort of the fluorescent coming out of this ball, these balls of sodium atoms. And the temperature of the laser cool sodium atom here is roughly 100 microkelvin. Okay. Now, out of these ensemble, we want to trap single atoms, and we want to trap it using a technique, using a tools called optical tweezer. So what are optical tweezers? And I think many of you are also familiar with. In different contexts, optical tweezers was invented by Arthur Ashkin, who won the Nobel Prize in 2018 in physics for such an invention, can trap atoms, molecules, and dielectric beads, things that can be polarized essentially by the laser beams. So basically, laser beams are very fast oscillating electric fields. It can polarize these objects, atom, molecule, and dielectric beads, and often that these objects, these tiny objects, can be trapped at the focus of the lasers. Okay, so so now our setup is the following. We have a microscope objective. We shine laser beam into the vacuum chamber and overlap it with an ensemble of laser cool atoms. So in previous experiment prior to this work that I shown here in 2001, now a while ago, that all these traps usually trap, or at least in terms of for the atoms, it traps an ensemble of them. Because as you are, of course, familiar with, when you try to grab atom molecule or you try to use any scientific instruments, it's rarely, it was almost impossible, if you think about it, very difficult to actually have just one atoms. Usually you have an Avogadro numbers of atoms or molecules. So how do we get just one atom? Well, it's actually quite remarkable. So if you focus this beam down to very, very tiny spot, something like on the order of micron, and overlay it with the ensemble of laser cool atoms, then you can grab single atoms. So what I'm showing you in this video here is 3 optical tweezers. And as you can see that these bright spot kind of blinks on and off, and these bright spots are actually single atoms. Maybe let me play it again. And this loading process, as you can see, is stochastic, and that's why sometimes you don't, even though there's an optical tweezer here, at this moment we didn't see a single atoms. So as we focus these laser beams down to very, very tight spot on the order of submicron, it's such a small volume that if we have pairs of atoms that falls in there, cools into these trap, then they can actually absorb another photon that are present due to the presence of the laser cooling beams, such that they get excited and then they get ejected out as pairs. Okay, so this process, as demonstrated in this work, has a pairwise rejection. So if you happen to load even number of atoms, then they're pairwisely ejected, you end up with 0. And if you load an odd number, then you end up with 1 atoms. Okay, so this process is stochastic, but it can be made to be not stochastic by some rearrangement of the optical tweezers. So here I show you some also fairly recent results in the field where perhaps we can focus on this image where we have, maybe I should count here. Yeah, we have 10, there's in fact 10 by 10 tweezer, 100 tweezer here. And because the loading process is stochastic, you can see about half of the sites are loaded. In order to have no vacancy, one can take an image like this and in real time move, for example, after 53 moves, they can make a compact up single atom array to the following image. You can do this in many different geometry. For example, if this is the geometry you want to order your atoms, or these other, for these ones that has these more honeycomb looking lattice, you can do then with very high fidelity, both in 2-dimension or 1-dimension. Okay, so this is something that's really cool, and that has huge amount of enabling possibility ongoing for now. Okay, in our experiment, what we're interested is not just trapping one species, but rather 2 different species. So we need to have a way to control then, control the individual atomic species differently. And the way we realize that is using different colors of tweezers, because the different colors will talk to the atom due to their particular energy levels, their specific energy level of the atoms. It will talk to the different atoms differently. Okay, so again, we have 2 different tweezers, different color, shining into a vacuum chamber and overlap it with an ensemble of sodium and an ensemble of cesium, so that we can grab single sodium and single cesium inside from the ensemble. In these experiments, we can repeat many times. We can take histogram like the following. And we can see that what is our success rate. And when we take histogram like this, maybe I'm getting ahead of myself here. When we get the histogram like this, we can draw a line saying, most of the time, well, not most of the time, but most of the time we have a peak over here that actually corresponds to 1 atom. And the remaining of the time we have 0 atoms for that site. And we can put this threshold there very clearly to distinguish whether we have loaded 1 atoms, like in this case, or no atoms. Okay, we do the same for both sodium and cesium. And because, like I say, the process is stochastic, we have, say, 33% of the time where we loaded both a sodium and a cesium in a single shot. And which is actually the highest probability compared to if we just load 1 species, not the other, either cesium or sodium, or none of the species. Okay, so in the shot where we have both species, that's a good starting point that we can actually make a molecule out of them. But they are really far away compared to what you would consider a molecule. They're in the lonely atom club. So in order for them to have a chance to meet, they had to first be brought together. And that is done by, as I show you in this video, by steering these optical tweezers with electronics, basically. Okay. Now comes the challenge. Even though they are in the same spot, to actually make a molecule out of 2 atoms is actually not that easy. And the reason is the following. So if we have a molecule, we have a pretty well-defined distance between the 2 atoms inside the molecule. And that would be, say, on the order of 0.2, 0.1 nanometer. But if they're not a molecule, they're just a single atom, even though we have two of them in a trap, in an optical tweezer, which provide a confining potential, holding that we can hold them in space. Even the best case scenario where we cool these atoms all the way down to its motional ground state, quantum mechanical allowed motional ground state. The uncertainty associated with this particle is actually about 50 nanometer in sort of the worst direction. So we just couldn't pinpoint where that atom is, this is the quantum mechanical natures of things. We couldn't pinpoint the location of that atom to, 50 nanometer. And if we have two of them, then the probability of finding two atoms, which each one with a wave function spread, each one with an uncertainty of 50 nanometer, to these kind of distance, that probability is it's 10 to the minus 6%. So it's very, very unlikely you'll find two atoms at the right place that they can make molecule. Moreover, to make a molecule, we have to remove the binding energy such that two atoms can come together and form a molecule. And that, if I put on the temperature scale, is thousands of kelvins. And of course, thousands of Kelvin is much, much higher than microkelvin. So if we have already cooled down the atoms to microkelvin, and we want to end up with microkelvin temperature of molecule, this 6,000 Kelvin energy has to be removed. So the main challenge, simply put, is the efficient molecule creation while staying very cold. Okay, so this actually, in the last 10 years or so, there have been solutions that put for actually was work done when I was a graduate student in July. And this has a two-step approach, has a two-step solution. First, first the atoms can be, instead of going all the way down to the low vibrational ground state where their spacing, between the atoms is very, very close, we first go into a state where there are a molecule, but vibrationally highly excited, so that they're all the way up, similar to atom. I mean, they're not that similar, but they're certainly closer in size compared to a low vibrational ground state molecule. And that can be achieved by utilizing a very special property of these atoms, which are alkali atoms that has these scattering resonance of that can be tuned by magnetic field. So by tuning magnetic field, we can associate them into a weakly bound molecule. So schematically, these resonance can be represented by sort of two energy crossing as a function of magnetic field. And these crossing is avoided crossing because there's coupling between the states. So as we ramp the magnetic field from one side of the resonance to another side of resonance, we can smoothly ramp the atom into molecule. Okay, experimentally, I show you a result that was done in the case of sodium and cesium with single atoms to begin with. What we're looking at is imaging of atoms, and that's the capability that we have. We couldn't cycle photons on the molecule, so we had to image the atom. So at the beginning, we have the atoms, we can image them. And once we sweep the magnetic field, we saw these, a large population, a large probability, large population of atoms have been removed, or at least dark. You see these difference. And that's in fact making the molecule. It's just that these molecules are dark to our imaging light. We can only fluoresce on the atoms in this experiment, so they look dark. So what we can do is to reverse the process to make sure that they can be returned to atoms, and then we know this process, we didn't lose the molecule, it's just that they are in the dark imaging state. Okay, so that's the first step. The second step is the following, where now we have made these weakly bound molecules, but not quite where we want them, which will be all the way down to the energy landscape bottom, the rotation, vibration, electronic ground state. And to do so, we have to remove that large amount of binding energy, and that is achieved by using a 2-photon transition to take away these energy. So basically, the stimulated photon take away the excess binding energy, and that 6,000 Kelvin worth of energy is not deposited into the particle or the gas. Okay, so yeah, so let me get into a little bit more details. Now, that's sort of the general overview of how we do it. Specifically, this is how we actually do it in the case of sodium cesium. So it turns out these molecules that we made, they're weakly bound molecule. We call them Feshbach molecule because these resonances are called Feshbach resonances. There actually has a spin characters of triplet. The low vibrational ground state molecule and electronic ground state has a singlet characters. So we had to find an intermediate state such that we can bridge not only the size mismatch of these two different distinct sizes of molecule, but also changing the spin character. We chose this particular state as drawn here because in these potential, the wave function or the place where the molecule will spend the most amount of time, where their overlap will be the best, is actually at the turning point. This is where you can imagine if you have a potential and you're rolling a ball, the ball spends more time when it's turning around. So it's very similar in this case. So this is where the molecules spend more time, as well as over here. So that's where we want to allow the overlap between our initial states and the overlap between these intermediate state to the final states. Now I say to shine 2 photons at it. In reality, it's much harder than just shining 2 photons at it, because for the system to be well described by these 3 levels, 1, 2, and 3, first, they are bridged by these very different color of lasers. Second, that these laser has to be in sync. Okay, so that means we have to control the laser very precisely, so they're in a well-defined sort of oscillation between the 2 lasers, and that we lock to a very high Finex cavity, meaning that we have these mirrors on, at space by some spacer, and that the light will bounce back and forth in between there many times before it will actually come out. So that has very high coherence. Okay, so this is what we do when we shine just one laser to look for spectroscopically looking for this state. We found it, and we identify a particular one with its quantum number. I will spare the details, and that allow us to couple down to the state that we want. Okay, so to look for these other states, we have to scan laser so that it can talk to that particular states. I will skip some details just to say that when we have 2 lasers on simultaneously and locked to the cavity where the phase coherence is well preserved during the time scale that we shine these lasers, which would be on the order of a few microseconds, we can see a dip of our atom signal. And again, when we see a dip, now it's because we have successfully created a molecule down here, and they are dark to our imaging sequence. Okay, but we can also shine these laser on for a variable amount of time, which is plotting on the x-axis. And what we see is actually an oscillation of the signal. On top here is where we make, starting with these weakly bound Feshbach molecule. And at the bottom where most of the signal goes away is where we actually create the low vibrational ground state. So I want you to kind of connect this picture to the ticking of the clock that I showed at the very beginning, that basically our system now is not the S and the P states of an electron in an atom, but our states are these two molecular states, and our ticking of the clock in this case is the weakly bound molecule and the low vibrational ground molecule. So we can connect them with these two photon lasers, and the ticking could go on between these sides, these vastly different size of molecule. Okay, so to close the loop from exactly two atoms, I show you if through stochastic encounter, the probability of finding two atoms at the distance that we will be able to make molecule will be 10 to the minus 6%. But because of all the quantum state control that we can apply, utilizing, kind of really the efficiency of quantum mechanics, is that we can make 30% of them into these molecules. And this number can, in principle, we believe we can increase quite a bit more. We hope to be able to reach in more like 80% by just, stabilizing our system a little bit more. Okay, so these molecules that we made in holding by the optical tweezer can live on the order of seconds, or at least a second. They can be there a second. We couldn't measure longer because our experiment is run into some other technical limitations, but that can be also overcome in the near future. Okay, so now one of the things that would be interesting to see, like to understand, is what is the limitation, perhaps, is there any limitation to the time scale other than our current experimental capability? Well, we can make them go away much faster if we turn on the intensity of our tweezers. And that is because that the tweezer still talks to the molecules. It can, even though off resonantly, it can still scatter photons. So if we have very, very intense beam, and in this case, a factor of, let's see, a factor of 10 to 30, then we can, sorry, I guess in this case, a factor of, anyway, a factor of 20 or so, then we can make them shorter by the fact that they off resonantly scatter. Okay. Now, with one molecular qubit fully control, our quest to gain total control of a single molecule is successful. We're ready to parallelize the process to unleash the power of the single molecule. I call them the single molecular qubits, by scaling up the system and entangle them. Okay, so what I'm showing you here is our first attempt to scale up. All the things that I described to you can be done in parallel if we start with more optical tweezers to trap the single atoms, and pairwise, in parallel, assembling a molecule out of two atoms in a parallel fashions. So what I'm showing you here is a stochastically fill single atoms, and here we have 9 traps, and 5 of the traps have fill single atoms, and we can do these rearrangement to compact up the single atoms into one side as a good starting point to make the molecules. Okay, so now these single molecules are well isolated. they're well isolated, which is by design, because we don't want them to perturb one another until we want them to talk to one another through dipole-dipole interaction. But can we do an experiment where we actually bring them together and allow them to meet? Okay, so what if we allow these two molecules to meet? What would happen? These are very, very cold temperature. It was actually quite surprising, actually already some hints from 10 years ago, and we sort of verify it, be able to directly observe in the last year or so, that when this is a different species of ultracold molecules, again, they're made from the alkali atoms and using very similar techniques, but they're made in bulk, but they can meet pairwisely. When two molecules meet, these are sort of, again, microkelvin temperature molecules, they can chemically react to turn into, in this case, potassium dimer and rubidium dimer. And what was really remarkable, or actually quite surprising, was that because they have been prepared at the lowest temperature energy states, both motional degrees of freedom and all the other degrees of freedom, and that the energy, the exothermicity, the energy release of such a chemical reaction is very small. While they have to transient through a very, very deep well, they actually get stuck in this transient intermediate K2RB2 star for a very long time, and much longer than we would typically think of a normal chemical reaction. So we measure this time scale to be on the order of microseconds, while usually we would expect them to be more like picoseconds. So this is actually very exciting because now we have a way, at least in these experiments, in these type of chemical reaction species, to really probe the transformation of chemical species from one kind, KRB, to the other kind, K2 and RB2. And moreover, we've also found what was really also surprising is that usually when we change, we try to influence a chemical reaction, we try to influence it by changing something about the reactants. But now, because these intermediate live for so long, we can shine light and drive away these intermediate to some other excited state and change its, basically steer it away from its natural course of reactions. Okay, so and then we actually do a lot of really other interesting study with this very specific system. So let me just summarize. I've told you the exquisite quantum control that we have on molecules, and we are thinking about a variety of quantum science application. Ideally, we tailor the molecular species to the specific quantum science application that we're interested. In particularly, we build a single molecule, we build a fully controlled individual molecule, molecular qubit, that we will use to harness their intrinsic property for quantum computations. I've only very briefly described that we brought these, to enable this experiment, we need both these more physics type tools and also chemistry tools to probe them to characterize these reactive process at these very cold temperature. And we are in the process of understanding them completely by treating them as a quantum mechanical question and see if we can describe it completely using that language, and to see if we can further harness it to generate some very valuable quantum resources such as entanglement. Okay, so with that, I'd like to, at the end, last but not least, to thank the people who did all the work. Here's a picture of my current group, and also people who have came through the lab and now move on to other positions. The specific experiment on the optical tweezer assembling of molecules are work done by people down in the bottom row here, and the newcomers over here. Okay, so I also like to thank you for your attention, and I'd be happy to take any questions.
Thank you, Kang-Kuen. We do have time for some questions. Zoom participants can ask questions by raising their hand and or typing their question into the Q&A panel. And if you raise your hand or type your question into the Q&A panel on Zoom, I will call on you. I will unmute your mic and you can ask your question. If you are not interested to ask your question directly, just put in your text to tell me to read out the question and I'll read it out loud. If you're viewing on YouTube, you can enter your questions in the YouTube chat box and they will be relayed to me and I will read them aloud so that everybody can hear them. And with that, let's see, we have a question from Charles Clark. Charles, can you unmute your mic and ask your question?
A very fine talk, Professor Nee. So since the laser appeared as a tool of atomic physics, maybe this was in the 1970s, there was a long dream of making laser-controlled chemistry possible, being able to drive chemical reactions in arbitrary directions. And your colleagues at Gila and you have done that in these well-controlled experiments. I wonder if you could just, like in a few words, summarize what were the key scientific developments that made it possible for you to do what you've accomplished today. And you went over them, as I see it, quite well, but maybe you could just give a quick summary and perhaps speculate about where the next breakthroughs will come from that would make one able to control chemical reactions of industrial importance, for example.
Yes, thank you so much for the question. So, as I was trying to describe, that this techniques, of course, is very specialized. We want to control all these degrees of freedoms, and we do it starting from atoms, and then we map that degrees of control we have of the atoms onto molecules. So in terms of how generalizable such a technique, I think in terms of assembling a molecule made of 2 atoms, I can imagine probably we can assemble a molecule made out of 3 atoms. As a sort of the next step. But sort of in parallel, there's the lot of efforts also working directly with cooling of molecules. And I have kind of alluded to that this has been difficult, but in fact, in the last 5 years or so, there's also a lot of progress made on laser cooling of molecules, and especially recognizing that some of these molecules, the key factor is that you have molecular structures such that you have a cycle, you have particular atom that you can use to cycle photons while leaving the rest of the molecules untouched, and therefore you can attach a lot of things, like things that has a large number of atoms into such a molecular system. So then as a way of cooling the molecule. So I think these different techniques are kind of going hand in hand. We sort of help push each other to continue these quests for more control of the molecule and more diverse ultimately. And I guess I see the next breakthrough may be to really on the one hand to go for diversity, and on the other hand to continue with the roots that we started out with and thinking of new possibility that we can actually harness chemical reaction. And I guess to kind of finish that is that one of the idea that I didn't get into, but that you may be interested, is that we think we might be able to use chemical reaction to generate entanglement pair the reaction products could be end up to be entanglement pairs. And so that would be a completely new application that we didn't think of before. And now we think there is such possibility.
So is it appropriate to say that atomic physics remains the one ring that rules them all?
If you put it that way, yes.
I don't know. I think you might want to be careful about that. We have a question coming from the YouTube, which is a bit of a follow-up question, I suppose. Will Angel asks, so what does a pathway look like to commercialize the laser construction of molecules? And will this ever be cost competitive with other industrial chemistry techniques? Which you might modify to say what will it perhaps be competitive with other industrial chemistry techniques?
Right. So no, it's not going to be compatible with the industrial technique. And this is not the way to make really, the molecule for, drugs or anything. I mean, this is really a quest to get to sort of the quantum mechanical nature that we want to exhibit. And also, like I said at the very beginning, we want to use these molecules as they are quantum machines. And they're more complicated compared to atoms, which are now, they are a commercial company to use it for sensor, but also for quantum computing, these things like people are developing. But we're just imagining that more capability can be realized, if we have at hand a well-controlled system that have more knobs to begin with. Certainly harder to control at the first, but we, the hope is that these different degrees of freedom can all be harnessed. I guess one very specific example that I'm hoping to contribute is that one of the issue about entangling of atoms or entangling of qubits for quantum computers, let's say, to make it a viable system, is that the fidelity is limited. And some of these limitation comes from the fact that we had to mediate the interaction by doing something to the qubit system. But that's a lot of classical control problem. But if we have a way, I'm thinking about molecule where these interactions are more intrinsic. Our job is to control it so that it's in the right state and then take off of hands so that it can do its work. It can do its coherent evolution. Then things could be more coherent, higher fidelity, and then we come back and read it out. So I guess that's what I see. Where we're going with these technologies, not to necessarily, not so much to make the molecule for the application of exotic material or for drugs, but perhaps for the kind of quantum computing, quantum simulation system that will allow us to do the computations.
I would ask a question, then we have a question from Carl Merrill. So you showed a couple of resonances and you were talking about atomic clocks. And I got to wondering whether the resonance going back and forth between the molecule state and the single atom state, I think is what you showed, whether that's regular enough to make a clock and whether the accuracy of that clock would be comparable to what we have.
Yeah. So so that's a very good question. Not in our system because they are actually people, for example, Tanya Zelominsky at Columbia, they're trying to, they are indeed making molecule, in their case, strontium. So these strontium dimers, so these are molecules that have atomic or molecular transition that are extremely narrow so that they can drive system with very long coherence time. So certainly not at the moment, I would say, that it's anywhere near competing the best atomic clock, or even the the standards currently. But but we're interested, as a whole, as a community, we're interested because molecules sometimes have, certain molecules have different kind of sensitivity. So we want to have a clock that's sensitive to a particular particular physics. So therefore, we built something so that we can make measurement of that, not necessarily for the purpose of timekeeping, but just
Right.
to be very sensitive to something that we wanted to measure very, very well.
Carl? You need to unmute your mic, Carl.
The lecture was a spectacular tour de force, but I couldn't get a real feel for how much of it is really manipulative by the operator, that you have to actually move things around, or how much of it is actually controlled by a computer. And if it's not controlled by a computer, it looks like there are so many variables: the intensity of the laser, how many particles to fire at it, etc., that it would be almost impossible. I didn't get a feel for how that's accomplished.
Yeah, so these experiments are controlled by computer completely, but things sometimes go out of alignment, and these kind of things we had to go back and tweak it. So our experiment, for example, that one curve, nice oscillation that I show at the very end about these weakly bound to low vibrational ground state, that actually takes 8 hours to take. So it was taken overnight. The students were sleeping. The experiment is running automatically. And then we are hoping, because we have been working with one molecule, we're hoping by going to 10, our speed will going 10 times faster, so that we will be able to take data much faster, and we will be able to use them much more before things go out of alignment. So the I guess long answer short is that it's all completely controlled by computer. And as much as we wanted to.
So if that's the case, does the computer learn to do that control by learning, or is it by quantum mechanical?
Yeah, not quite at that stage. Yeah, and then, like I said, sometimes we do still need to go there and tweak things so that things are good. But it would be good, yeah, if everything could be more automatic. I mean, especially yeah, especially during now we have limited density to be in the lab, or even for a period of time we're not allowed to be in the lab. Like, being more automatic is good, so that things could continue to progress even when we're not allowed to be in the lab physically.
But that means the control is not done by using first principles and doing quantum mechanical calculations. Is that correct?
Right. I mean, so far I would say all the physics, if we can try to model it, I would say, like what we expect to get and these kind of things, we know what we need to get. It's just a matter of how we can get there. Yeah.
Thank you.
Thank you.
We have a question from David Rabinowitz. What are the limitations to the pairs of elements which can be combined? And can you produce molecules that would not normally exist in nature?
Yeah, that's a very good question. And I think, yes, we should be able to also make molecules that not normally exist. They certainly wouldn't exist at these kind of temperatures. So in that regard, we have check that box. But in terms of what can be combined, because our technique right now, as I lay it out, that we need to start with laser cooling of the atom as our very first thing. So it need to be laser coolable. But luckily, there are about 25 elements on the periodic table are laser coolable. So you can imagine, like, one could start from there. But certain techniques, certain steps along the way could be challenging in general. But I think if there's a good reason to do it, we could do it, basically. Yeah.
I apologize, David. You might have wanted to ask your question with your microphone. So if you have a follow-up, please unmute and go ahead and ask a follow-up question.
No, thank you.
Okay, we're good. I guess another question is, have you seen anything in the experiments that you've done empirically that lead you to question any aspects of quantum mechanical modeling that you have applied to understand how these experiments are supposed to go?
Not actually. Quantum mechanics is fine. Yeah. But I guess I do want to say that in an experiment that I didn't discuss too much in detail, to study the chemical reactions, we are now able to experimentally characterize the chemical reaction process in detail, especially looking at the reaction products and their quantum states. And I would say that that is actually a problem that we don't have the computational power right now to calculate exactly. Although we can measure exactly, there is some notion of what we would expect because there is a very long-lived intermediate complex, and therefore we should kind of expect that the quantum states are all kind of equally likely to be distributed. And we can check that, that assumption, or that very grossly simplify yeah, the predictions, and we have seen sort of preliminary some deviation. So it is calling that we would need more computational power if we want to understand exactly everything, but that is not saying quantum mechanics is not right. It's just that we are not able to calculate it because just because we can write down
Have the
Schrodinger
computational
equation
power.
doesn't mean we could calculate it. Yeah.
Yeah. So does it go the other way at all, that the empirical results in your observations are useful to semi-empirical methods of calculating quantum mechanical models?
Yeah, I mean, I think it will certainly provide a benchmark, right? So in some sense, in terms of spectroscopy, often we would have a combination of ab initio calculation and spectroscopy to get a better prediction of sort of the next spectroscopic lines. Yeah.
So another question, this is kind of an odd question. I don't know if it really makes sense, but usually chemistry you're doing with, significantly large ensembles of molecules, and there are a lot of statistically determined outcomes. Like there's always a certain, stochastic nature to chemical reactions. And I just wondered, when you're doing these experiments, and maybe you really haven't done enough of them, but when you're doing a whole series of them, do you see that variability paralleled in the outcomes of what you're doing? Or are yours really determined?
Mm-hmm. Yeah. Yeah. So, yeah, our system is certainly very different in the sense that when we want to have, say, two molecule collide, I mean, we have experiment where we have exactly two molecule collide by putting two of them in the optical tweezer, or we can have then very low density. So that's the dominant process. What is really different from conventional chemistry is that when for example, I was showing you when the reaction goes from reactant to product going through these long-lived intermediate states, we have nothing else to collide with it. So that's not happening in general, but the light can interact with it. So that's something interesting. So that's, for example, one aspect that's very different. So people always say, why doesn't it just fall down to the bottom of the potential? Well, there's no way that it could do that. It has to have, we have to account for every single event in some sense. We have to account for the exact process that things could happen. And that's kind of the regime that that's the kind of regime that we are doing these experiments. It's like we try to understand and every little detail basically.
So I'll ask one last question. And this one also might be a naive question, but I usually think of a qubit, it's got two states, 0 and 1. Your molecules have an awful lot of of degrees of freedom. So is it possible to encode within all those degrees of freedom, multiple, not just 0 and 1, but, a whole
Yeah.
series of qubits within one molecule using
Yeah.
all the different states?
Yeah, I think that actually speaks of the power of molecules. So maybe not so much the different degrees of freedom, but even within a single degrees of freedom, there's not just two states. So they are actually, for example, the particular molecule sodium cesium that we're working with, the hyperfine state in the low vibrational ground state, they're actually exactly 32. So you can imagine that's 2 to the 5, and you can encode information that way. But how you would be able to bring them out and utilize
that's a
them,
trick.
that's the questions. So the complexity comes with yeah, I mean, it's a blast. People like to say it's a blessing, but it's also a curse. Like you had to you had to control it all to know how to use it. Yeah.
Well, we got another question from Charles Clark. So
Yeah.
Charles.
So I wonder if you could comment on how the fundamental research in this area has benefited from other developments taken on for other reasons, particularly laser technology. I remember Eric Cornell telling me that the development of diode lasers for telecommunications revolutionized the practical ability to make a Bose-Einstein condensate. You didn't need 5 graduate students to operate 5 lasers, but you had a reliable solid state component. And then the blue laser that got the Nobel Prize, and I guess as recently as, was it 2014, maybe even later. That was another revolutionary development undertaken for completely different purposes, but it's had a great impact. So do you feel that you're sort of riding the wave of developments in very high-end technology?
Yeah, that's a very good question. I can't think of a very specific example, but certainly, our experiment consists of at least 20, 30 lasers. So it's very difficult to control all of them if they're not working properly. They're not some reliable technology. So, I mean, I would say, for example, I think our sodium lasers, it's a solid state system that may have been developed for guiding stars.
Oh, yes.
Yeah, so that may be one example. And then we have, different things that we do, like wavelength doubling and things like that, also for sodium, for example. Some of that, I'm not sure what they were originally developed for, but we're definitely, like, these are kind of new technology that makes the experiment much more manageable.
Yeah, but these were adopted technology. These have been developed by others, and the scientific applications were then found.
Right. Yeah, is there anything that you can think of? Other examples?
Well, I guess you've named it. Yeah, the sodium guide star lasers, another, fantastic development. Again, developed, I think, largely developed by the Air Force in some extent for doing what do you call it? Adaptive imaging in atmospheres.
Imaging, yeah. Right. I mean, we do have this other laser system. I'm not sure what it's developed for, but in our one experiment, we have a YAG pulse laser that's traditionally sort of 10 hertz, and we have it for 100 kilohertz. so that really increased the repetition rate of the experiment, of course. And I'm not sure what it's developed for, but we're, this is also a technology in the last 5-10 years.
I'm wondering, is there a particular reason you're asking that question, Charles? It sort of reminds me of Jerry Oistrakher's book on on how the money coming from the Defense Department primarily sort of channeled the sorts of experiments that were done in physics because of the instrumentation that was available. So I'm just wondering why, if there was some particular reason you were asking about it.
Well, I guess there is sort of a personal recollection. When I first visited Bill Phillips' labs at NIST in Gaithersburg, he was doing laser cooling and trapping of sodium. There were these dye stains all over the laboratory with these dye lasers. The hoses would occasionally break and just spew
Right,
this
yeah. Okay.
rhodamine 6G all over the place. And there may still be some such lasers operating in certain like
Yeah,
that.
we
in
have
certain
rhodamine
laboratories.
6G in our experiment, but that's for that's for our sort of the more universal detection of the molecule, and then that's what the dye laser is good for. So if we're trying to control the atoms, things are more like well managed. But when we try to talk to molecule, a variety of different sorts, then we still need this rhodamine 6G probing. Yeah. So maybe some kind of technology that will replace that, but still, widely tunable, like the dye laser, and it'll be really, really, really useful for molecular research.
Well, I guess also the optical frequency comb is a key tool for you, is it not? Because
We actually don't use it, but at the
Oh.
very first demonstration, yeah. So
The
we
first
use optical
demonstrations, yeah.
cavity. We use just optical cavity. Yeah.
So I think the last question is really the last question, but it's I'll sort of interpret it. I think the questioner is asking you whether in your experiments in which you're looking at quantum states of matter in a very detailed way, have you seen anything, given the current state of physics, have you seen anything that leads you to, say, embrace the many worlds theory or some other of the theories that are floating around about the nature of the physical universe? Or is this, say, not quite so grand and it's immediately appreciable?
Yeah, no, we're not doing these tests, I guess, tests of this theory. Yeah. We're more kind of believer of quantum mechanics, not so much the philosophical aspect, but just like how can we leverage it to use it, or leverage it, or to be able to see it. And like, one other powerful thing about the atomic molecular physics is often these visual aspect. We can take an image of the atom. We can, if we have just one atom, we do, we and in the superposition of states, every time we measure it, it can only be in one state. It's collapsing to one or the other. But then if we repeat many, many times, then we can see that it's in the superposition state. 50% of the time in the down and 50% of the time in the up. So those things are, I think, very cool, and there's something that we use it, but we don't. Yeah, our experiments are not for testing these kind of more perhaps philosophical questions.
I think it's enough that it's a stupendous achievement to be able to do what you're doing and
thank you,
and extract information and be able to manipulate single atoms is certainly not something that when I was going to school anybody thought we'd be able to do anytime soon. And so it's really remarkable, and we'll leave the practical implications for later. But for right now, it's a beautiful thing to be able to probe matter on that scale with that sort of precision. And we thank you very, very much for sharing your
thank you so much for the invitation.
So we really appreciate it. And with that, all I can say is thank you again. And I guess we'll turn to the end of the evening here. The recording of tonight's lecture will be available to everyone on the PSW Science YouTube channel and in due course on Vimeo and via the PSW Science website. Please share the link with your friends and subscribe to the channels for notifications on new postings. Before you go, we have a few important notes. I lost my controls. Okay, we're back. Sorry about that. The spring lecture series begins in 3 weeks with the 2,432nd meeting and the President's Lecture on January 8th, 2021. The speaker will be Michael Saylor, Professor and Director of the Institute for Materials Discovery and Design at UC San Diego. His lecture will be on recent developments in material sciences, particularly in the field of nanoparticles for medical applications, such as those used in the Pfizer and Moderna COVID-19 vaccines. Our speaker on January 22nd, 2021, will be Allison Hill, professor at Johns Hopkins University. She will be speaking on the mathematics of epidemics and its use in modeling epidemic and pandemic disease spread. And on February 5th, Avi Loeb, distinguished professor at Harvard University, will be speaking to us on the search for life and the likelihood of extraterrestrials, including ones smarter than us. He'll be addressing the question, are we the smartest cookie in the cookie jar? Check the website often for updates to the schedule. And with that, let's thank tonight's crew, James, Ann, and Robin, for producing tonight's event. I will now adjourn the 2,431st meeting of the Society. I wish everyone a good evening. I wish everyone a very, very happy holiday season and a wonderful new year. And I look forward to seeing you all in January 2021. The meeting is adjourned.